we've been asked to find the equation of the tangent plane and normal line to the surface x squared plus xy squared plus y cubed plus z plus 1 equals 0 at the point 2, -1, 4. Okay, now just some reminders here. So we're going to be finding the tangent plane to the surface. So you have a surface, alright, so you have the surface there. The tangent plane would be like a flat piece of plastic, paper, wood, whatever it is that you use to touch a certain point, this point on the plane, and a vector on it would give a certain gradient, well, a gradient to the plane at that point. All right. Now, of course, when it touches that point, the difference between the gradient of the tangent and the gradient of the point would be 0. Right? They would have the same gradient wherever you touch it, even though the gradient of this tangent would not necessarily be 0, but you have the point of tangency right here. You remember that when we generally found a stationary point on a curve, two-dimensional curve, that point was where the gradient equals 0. And what we did was to find the gradient function of the tangent and equate it to 0. And that gradient function was the derivative, like dy by dx, right? Now what we need to do here is to find that gradient vector, right? The gradient vector of the function would be, now to find it, oh, I said dy by dx here, this should be dx. To find the gradient of a tangent, you differentiate because you're looking at rise over run. So in this case, it is the partial derivative of the function with respect to x, the rate at which the function is changing as x changes, in the direction of x, right? Now, we could say it is x minus x naught, right? But since it's a vector, let's use I, j, and k for the direction. If you have the x-axis, the y-axis, and the z-axis, the x-axis in the direction of I, my direction is shown by I. For the y-axis, direction is j, and for the z-axis, the direction is k. All right. So here is partial derivative of a function with respect to x, I, plus, and then the partial derivative of a function with respect to y in the direction of a change in y, right? So I is the direction of a change in x, j is the direction of a change in y, plus the partial derivative of the function with respect to z in the direction of a change in z, which is k, right? So that is the vector. Now, we can therefore say the gradient vector f is equal to partial of f with respect to x and x minus x naught where x naught is going to be 2 from this point, alright? You can call it from ground zero, from that given point, plus partial of f with respect to y, the direction of a change in y minus y naught, right? Whatever y is, you subtract that position from the point y, which is -1, same thing with x. Whatever you have, wherever you have x now, the difference between, or the distance, which is the difference between the x now and the original x, which is 2, right? And then plus the partial of the function with respect to z, the rate at which the function changes as z changes, times the change in z, which is z that you have now, minus z naught, which is 4. So you see that? So there you would have the, you would use that to calculate the equation of a tangent plane. Alright? Now remember the normal line. So this is the TP, tangent plane. Now for the NL, the normal line. So here now, you use a parametric equation. You remember that the general equation of a straight line is y equals mx plus c, right? The m is a gradient. You could say y is equal to, the m would be rise over run. You remember that? So it really is the rate at which y is changing as x changes. So you can say y2 minus y1 over x2 minus x1 if you want. Should help you to remember the normal line equation. y2 minus y1 over x2 minus x1 times x plus a point c. But the change in y over change in x is really y is really dy by dx times the value of x plus c. So once you remember that, you remember the normal line equation. One of them is x equal, the other one is y equal, the other one is z equal. Now the x here would be replaced by the parameter t. Now you plus the point for x would be x naught. In this case it would be 2. Y naught is -1, z naught is 4. So plus -1 and plus 4. What then? What do you have here? It's the partial of the function with respect to x for the gradient, the partial of the function with respect to y for the gradient here, and the partial of the function with respect to z for the gradient here. Alright? You remember those. So, here now, what you can do is write down the question and write down the formulas that I reminded you about a while ago, and then find the equation of the normal, the tangent plane and the normal line for me. Okay, you finished? Finished doing it? Alright, nice. So let's see what's going to happen. Let's just repeat the equation here. x squared, the surface f equals x squared plus xy squared. The surface is function of x, y, z is really x squared plus xy squared plus y cubed plus z plus 1 equals 0 plus y cubed plus x plus 1. Alright, so that you have that. Now the gradient, sometimes called the grad, of the function is the partial of x with respect, is the partial of the function with respect to x minus x naught, plus the partial of the function with respect to y minus y naught, plus the partial of the function with respect to z minus z naught. Now what's the partial of the function with respect to x? When you differentiate, you're supposed to get 2x plus y squared plus 1. Alright? That's what you got. Oh, hold on, let me see something here. Oh, plus z plus 1, my. I mistakenly wrote x here and differentiated it. It should be z. So there is no 1 at the end here. Alright. And after that, the partial derivative of a function with respect to y is going to be, from this part here, 2xy plus, from this part now, it is 3y squared. Right? That's what you got, right? And then the partial of the function with respect to z is going to be, well, looks like it's just going to be 1 when you differentiate it. Alright? Now, what was the point again? 2, negative 1, 4. So, at the point 2, negative 1, 4, partial of f with respect to x is equal to, that would be 2 times x is 2 plus negative 1 squared. It will be 2 2s 4 plus 1, which is 5. Alright? Then the partial of f with respect to y would be equal to, y is negative 1, so this is 2 times x is 2 times y, which is negative 1, plus 3 times y squared, negative 1 squared. It will be 2 2s 4, 4 by negative 1, plus 3, which is 2. Okay? So, that's what you have there. 2 2s 4. Oh, 2 2s 4, negative 4. Oh, a mistake again, you know, because why do you think jump up all the way up here for? Yeah, because what happened? It's 2 2s 4 by negative 1, so it's negative 4. A mistake there earlier. So this should be negative 4 plus 3 is negative 1. Negative 1. Alright? Whoa. Okay. And then what happened here? The partial of f with respect to z equals for z. Well, in this case, the partial of f with respect to z, it was 1, right? 1, just 1. All right. Now, also, we know that x naught equal what, 2, x naught is 2, y naught is -1, z naught is 4. So we can write down the equation of the tangent plane now, right? So in this case we have partial of, let me write this, for this part, partial of f with respect to x is 5. So it's 5 times x minus x naught, right? So 5 times x minus x naught plus, then here the partial of f with respect to y is what? At the point it was -1. So it's -1 times y minus y naught. -1 times y minus y naught plus, then we have the partial of f with respect to z. What was it again? It was 1 plus 1 times z minus z naught. Alright? But then we can make a little change now. And we say this is 5 times x minus 2. Right? Minus 1 times y minus -1. But of course, y minus -1. Can write it as +1. Okay? Plus, you don't have to write this one here. But you didn't really have to write this one either, you know. It's just minus. Could just write the minus open bracket. And then this part is z minus z naught plus z minus z naught. Alright. So we can just open the bracket now. Simplify. This will be 5x minus 5 2 is 10 minus y minus 1 plus z equals 0. Equals 0. My. Right. This will be equals 0. Right. The tangent plane. As I said before, it right at the point where the tangent plane touches it. When you draw a vector on the tangent plane, it will be parallel to that point on the point of tangency. So the difference between the gradient of the tangent and the gradient at that point will be 0. So we say equals 0, right? Plus z minus z naught, which is 4, equals 0. So this would be now 5x minus y plus z, -10 minus 1, that's minus 11. -11 minus 4 is minus 15 equals 0. So you could write it as 5x minus y plus z equals 15 then. Alright? Okay, so that's what we have there. Now, equation of the normal line we want now. The normal line equations would be what? X equal, so let's write them out here since it's close to this. NL, normal line. X equal the partial of f with respect to x at the point. It was 5. So it is 5 t plus x naught was 2. 5t plus 2, and then y equals the partial of f with respect to y at the point was -1. So it's negative 1t plus, and then y was negative 1, so it's plus negative 1. And then at the point, the partial of function with respect to z was 1. So the z equals 1t plus, and the point z was 4. Okay. So the normal line equation, you could write it as x, well, the equations that represent the normal line. X equals 5t plus 2, y equals negative t minus 1, and z equals t plus 4. Right. Now, if you want to, or if you're asked to, you could write it without the parameter t. To eliminate the parameter t, you transpose this for t. So you're going to say, in the first equation, t would be equal to x minus 2 over 5. In the second equation, t is equal to, well, could write it first as negative t is equal to 1 y plus 1. So then positive t would be negative y minus 1. See that? And then for the third equation, t would be z minus 4. So t is equal to t is equal to t, which means x minus 2 over 5, which is t, is equal to negative 1 minus 1, which is t, which is equal to z minus 4, which is t. Okay? So, and if you want everything to be flat, no denominator, multiply by 5. So you'd have x minus 2 equals negative 5y minus 5, also equal to 5z minus 5 fourths 20. So that's what you would have there, right? Let me see, what else could I do? Suppose I add 2 to both sides. Just playing around with it. Suppose I add 2 to both sides. I could say x equals negative 5y, negative 5 plus 2 is minus 3, and that is equal to 5z, and then negative 20 plus 2 is minus 18. So you could very well write it like this too, right? Alright, but anyway, if you got stuck at any point, or you found it very difficult and didn't get the right answer, I want you to repeat your efforts at working it out. Alright? Remember now, if you're not subscribed, make sure you subscribe to the channel, share this with somebody else, and any questions, comments, and so, put it in the comment section. I will see you.